wanted to point something out here. It's a tendency that I do, is probably most professors do, and you have experience. When we tend to use overhead slides, we probably go too quickly. And so I noticed last time, one of the reasons that I've been trying to keep this down to about a half-hour max on the lectures is because when we roll these things up onto the web, I'm sure you don't want to sit there for an hour going, hey, that's just dribbling on. You know, when you want to go ahead and go through things when you're on the web. But I notice in the class, when we go through the overheads, we tend to go click, 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 and you don't have time to digest things. So as we get onto these slides, and if something comes up and you say, I'm not sure what's exactly going on there, you ought to just stop me and say, oh, wait a minute, I've got a question. Otherwise, what's going to happen is we'll go through these things fairly quickly. I really don't want to keep you here the whole hour. In a way, I'm trying to entice you to go to the web and to go through these things kind of at your leisure and your pace. Now, speaking of that, we haven't rolled these up yet, but we will as soon as this class is over. It turns out we had to convert everything to PDF and all that to roll up the PowerPoints. And then what I had to do was to compress the lectures, the things that we're taping here, because they're gigabytes. We had to use, I think I wound up using MPEG, which got it down a factor of 20, so now we're in megabytes. So you'll actually run through these things maybe 20, 25 minutes, however long they are. So anyway, I run through these slides because at least I want to acquaint you with what you're going to experience or what you'll run into when you go onto the web. Right? But certainly if there are any questions that come along, you say, oh, wait a minute, I don't quite understand that. Just ask me and then we can explain it here. Okay? All right, we're still on roots of equations. We talked about a bracketing method, an interval, two values last time, right, where we were doing either a bisection or we're talking about interval halvings. This time we're going to introduce this concept called an open method. It means you've got one value. And so from that one value, then you're going to try to do your forecasting or coming up with the estimate or the root or whatever the value would be. There are three commonly used methods. As you can see, fixed point iteration. The second is Newton-Raphson and secant. Now the secant method is a variation of the Newton-Raphson, but the one that I want you to focus on is this one, the Newton-Raphson. That's the most important one.
Okay. When you say you have one value, you mean like you have like a max value that it could be?
Not necessarily. Not necessarily. You'll see as we kind of go through and look at one of the examples. It's kind of like if I want to do a meteorological forecast and I only have one tower. And so I get that data. What I'm trying to do is predict the winds over the whole region. But I only have that one point. All right, that's the example of an open or a forward type of iteration or forecasting based on one data point. It doesn't mean that it has to be the exact value. It's just I'm going to try to approximate what I think it is. Right? You understand? It's a little bit hard to grasp, but you'll see it as we go along here, particularly on some of the examples. The examples that you have in this course are relatively simple. When you get into the real world, a lot of times that whole business of, gee, what is the forecast, or what am I going to be doing as far as the simulations? You know, where are they taking me? That's not so easy. And that's a whole field called optimization, inverse engineering, things of that sort. That's what you're referring to. Okay, let's take a quick look here at what we're talking about. In the bracketing, this is shown here on the left. That's what we talked about last time. So here is the function, right? There's the root. So what we're doing is bracketing this thing down, converging basically to what we say, okay, that's going to be the value as I do my approximations and let the computer program do the estimation for me. Right? This is kind of like, as I mentioned at the end of the last lecture, being a forward observer and dropping rounds down to where you actually hit the target. Well, you're kind of doing the same idea right here. Okay, now, when you talk about A, that's the bisection, you notice I have written up there, the root is constrained within the interval prescribed by the lower value and the upper value. All right, so you're starting with an initial guess of a lower and upper value. And then the computer is going to do this for you as you proceed in succeeding steps. Okay, in the open method, that's in B and C, all right? That's these two right here. You see what you're doing is employing, in essence, a derivative. That's the Newton-Raphson method, and what you're doing is projecting that from xi to xi plus 1, all right? So that's kind of the new estimate or new value. That method can lead to either a divergence or a convergence. Now, what do I mean by a divergence? What does it imply? It means no matter what you do, the answer is going to get worse and worse all the time. What you really want is a convergence, and you want to do it as quickly as you can. All right, now, of the three methods, let's look at the first one for a moment. It's called fixed point iteration. All right, so you have a formula, whatever that formula is to predict a root. What you're doing is verifying and confirming your numerical approach. Set the function f of x equal to 0. X is the unknown, all right? So xi plus 1 equals to whatever that function would be. It's a function of x. So the I plus 1, anytime you see things like this, like an I plus 1 or an n plus 1, it usually means unknown value. Generally, we set that on the left-hand side. All right, so here's an equation. So what we're going to do is solve that for x, all right? So as I mentioned before, let's take advantage of the fact that computers are relatively stupid. The only thing they do is turn switches on and off. It's how you put all those things together into the combinations, basically through the software and the programming that makes them intelligent, and in essence that you can use them to your advantage. Okay, so what the computer does, it uses what it previously defined or calculated. So it's always going to use the latest calculation. In fact, you have to go out of your way to tell it not to do that if you're using a particular technique that says don't use the latest one, use one like a previous or two steps behind that certain calculation. Okay, iterations are useful when updating new values from old values. That's what we mean by the iteration. So what we want to do is shrink that interval down, right? We want to get that as close to the answer as we can. Okay, so fixed point iteration converges if the derivative, that's supposed to be a prime up there. Okay, so g prime of x is less than 1, right? So the magnitude of the slope, remember what the derivative implies? A slope. Okay, so the slope of g of x must be less than the slope of the line f of x, equal to x, for example, from that last example. Okay, here's an example of pseudocode. Remember what pseudocode is? Okay, so it's kind of a fictitious code. It gives you a little bit of the logic as to what's going on. So just take a moment and go through that and look to see what's going on. All right, our estimate is the initial value. That's what that x of O is. We start with an iteration count of 0, right? First step. All right, you know what this is? What do we mean by do? Or what do we mean by end if? What do you think it implies? It's a loop, right? It's called a do loop. In Fortran, those are known as do loops. And so it says, do this operation until something is satisfied or something kicks it out of the loop. Otherwise, it's going to sit there and keep doing this. And sometimes we write codes that do that, and you wonder, why isn't this thing running? It's because we've got an error in here. So it has to kick out. You notice in here the iteration count has been updated, right? So we start from 0, now it's 0 plus 1, so this is the first true iteration. If x of r is not equal to 0, calculate that. If it is equal to 0, what's going to happen? Yeah, it'll go out of the loop. Okay. These are the so-called if statements, and it's in the logic. You do it all the time, you just don't realize it. If this is true, I'm going to do this. If it isn't true, I'm not going to do that. So I'm going to bounce out of this. All right? That's sort of what a pseudocode does. It helps you to logically think what it is that this procedure is doing. Okay, so here's a depiction of what we mean by convergence, all right, or divergence. So A and B, okay, so here's A and B, right, and C and D down here. That's divergence, that's convergence, using a fixed point iteration. Now, you can almost look at this and see what's happening, right? What's going on right here? As I get the approximations finer and finer, what's that going to do? It's going to converge in onto the point, right? That's the solution as it crosses there. That's a convergence. What happens when you start getting these values much further and further apart, right? The intervals. It's going to diverge, starting to get further and further away from the solution itself. All right.
Okay. Well, I'm not really understanding. So 2 of those graphs are convergence and 2 of them are divergence.
How do I go back?
Previous.
Okay, there we go. All right, notice that convergence, this is what I want you to look at. Notice that convergence occurs when the slope is less than 1. All right? So how do you know when the slope is less than 1? You can calculate that. Or you can have the computer do that for you. Right? And when you think about it, okay, if that slope is less than 1, I'm going to eventually come in to the solution. But if it's going to be greater than 1, what's that telling me? Oops, I've got a problem, right? Because the next calculation may produce an even bigger, a simulation where that slope can be bigger than what I just had. It'd still be much, much greater than 1. Right. Now, let's take a look at Newton-Raphson. And I want you to really spend a few moments on this. Let it sink in, because this one's really important. This one you will carry with you, even wherever you work in the future. Okay? It's the most widely used root finding formula. All right. It uses the tangent line as an initial guess for the root. Right? Actually, you're going to let the computer do that for you. Okay. It extends from the point to where it crosses the x-axis. Right? Now, there's good and bad, as we'll discover. This is the formula. So what it says is that the new value, x at I plus 1, is equal to the previous value, all right, minus the function evaluated at x of I, whatever that would be, divided by the derivative of the slope. All right? It's a very simple approximation. Who's it attributed to? So what you're going to do then is say, well, how do I get this? Right? Here's the slope, right? Here's the function, minus 0, right? Divided by this, all right? That's delta x. That's xi plus 1 minus xi, or whatever the sign would be, okay? Here's the interesting thing about this. It yields quadratic convergence. Now, last time we noticed what? Linear, right? So now we're an order of magnitude better. Quadratic convergence. This is pretty good, right? The number of significant figures of accuracy doubles with each iteration. That's what makes it so interesting. It's so good.
Is that bottom x supposed to be an I?
Let's go back. Which one?
The bottom one? That's supposed to be an I.
Yeah, that's supposed to be an I. See, computers make mistakes all the time. It's not easy. Okay, let's find the root. F of x equal to e to the minus x minus x. Let's start with some initial value. We'll assume 0. All right, find the first derivative. Now you can do this by inspection. All right, so we won't let the computer do this. How many of you use Maple? What do you think Maple will do for you?
Do this automatically.
Do that automatically for you. So it doesn't mean that you can go brain dead on mathematics. Right? It's just that Maple will do all this stuff for you. Okay, now calculate xi plus 1 from the formula then. Now here's the formula. Xi plus 1 equal x of I. Remember what this was? F of x of I divided by f prime x. That's what this is, okay? So here's what happens when we just program this. You run this as a MATLAB code or however you want to do it. So here's the iteration. Starting at 0, I have obviously 100% error, right? Totally wrong. First iteration, second, third, and fourth. Watch the value in 4 steps. So here's the answer, right? I have an error or a convergence here set to 10 to the minus 8. Basically, it means that I'm within that realm of accuracy of the exact solution. That only took 4 steps, right? How long do you think that takes on a computer? It doesn't, you can't even measure it, right? It's that fast. So it takes you much longer to think out what the procedure is and write in the pseudocode, and once you do it, and it runs on the computer, it's done. Okay, here are 2 methods of graphing the function e to the minus x minus x. All right, so here is at a, here's a up here, so the root at the point where it crosses the x-axis, right? Okay, and here's the root at the intersection of the component functions. So if you were looking at that part of the, you know, e to the minus x, or f of 1 of x is equal to x, that's what you would get if you wanted to break it up into various segments. All right, now let's go to the problem of the bungee jumper. All right, so what we want to do is find the mass of the bungee jumper. You remember we did this last time, doing the interval halving. So here's the function that we want to evaluate, right? So we've said it f of m is equal to, this is what we got when we set up that derivative, right? Remember of the equation for function. All right, so the derivative of this function must be a value with respect to the unknown m. Anybody want to take the derivative of that?
Not really.
Not really. So that's why you might want to try MathCAD, Maple, Mathematica, one of those other things, or you can sit down and kind of work it out by hand if you're so inclined. Okay? All right, so here's what you get for the derivative. All right, so it's a little complicated. Now, the Newton-Raphson method, all right, it will converge depending on the nature of the function, obviously, and the accuracy of the initial guess. So the best of all worlds would be that, gee, I know what the answer is already, let me guess something fairly close to it, or the answer, it will converge quickly. If I don't, it may take a long time, or it may diverge, all right? So the only remedy that you have is an initial guess that's close to the root. Now, as engineers, when you're doing a problem, you generally have a gut feel for what the answer should be, or what you should expect. All right? You want to try to kind of remember that. Okay? Now, on some functions, no doubt, no guesswork will work, no matter what you do. So you must have some insight with regards to the physics. What is the problem? Can anybody think of a situation where you have something that absolutely will not converge? Anything that's going to bifurcate, chaos, something that, no matter what solution you get here, it's going to immediately change to something else. It's a transient solution, something like that. A sine wave could be that way, right? Okay. You have to have some sort of feel and an expectation for what to expect from the solution, from the problem, right? So, one thing to consider, Newton-Raphson method may converge slowly, right? But it will attempt to give you a solution, right? So it may actually succeed in finding the correct root after some time. Now, when you remember the formula, what is the one thing that's going to give you serious heartburn? The derivative. Why is that? Because you're dividing by the derivative. What happens if it's 0? You've got a big problem, which means you're probably not going to be using the Newton-Raphson.
But then it'll be linear anyway.
Well, that's, how did you know that? Because you had insight into the problem. Right? Okay, so here's a graphical depiction of the Newton-Raphson method. The tangent to the function of f of x, it's extrapolated down to the x-axis, all right? So this is what's happening. So here's the function. Here's where I start with a guess, all right? And so what it's doing is it's saying, okay, here's what I'm going to estimate, right? So I'll calculate that value. So what's going to happen as I proceed step by step through here, right? This thing is going to keep working its way down as a tangent until it gets right, as close to the solution as possible, or when you say enough is enough. Here's what can happen if you get a slow convergence, right? Obviously, this is one that would be somewhat tricky. So if you're starting with a tangent up here, and you're going to go, whoops, I see that this is going to tend to bounce around quite a bit. What is the solution that I'm after? Wait a minute, this thing's already setting on 0, so this one is an example of something that can be a little bit troublesome for you with regards to a Newton-Raphson approach. Okay, here's a couple of more examples where you might get poor convergence. What kind of curve is this, by the way? What do we notice? It's an inflection, right? And an inflection means it's a cubic, right? There are other ways to go about solving these things, but this one is an inflection, all right? Likewise, you can see what's going on here in this one, right? You have what? Another inflection setting here. Here is really a multiple set of inflections, you might say. What's this kind of remind you of? You mentioned it earlier. Sine wave. Right?
Now, D's only got one, which means it should be quad. Why would that give poor convergence?
Because at some point, the derivative is 0.
Yeah, go ahead, tell them.
At some point, the derivative is 0, and there's also no root.
Exactly.
Oh, okay, so it'll convert and it'll just zero out.
Yeah, so what, yeah. Once you start getting the f prime of the derivative in there where it says, this is almost 0, computers don't like that. So you could have suddenly, if you have a very small number into some other number, what happens? You get a very large number. Okay, here's an M file. So this is a MATLAB file. All right, so here's some descriptions, what's going on. As you can see, there isn't much code to it at all. On that. And so this is kind of tied back to that pseudocode. So take a look at the pseudocode, and then you can go, oh, from the pseudocode, I see that's the Newton-Raphson right there. All right, so it's fairly simple. All right, now let's talk for a moment about the secant method. All right, so it's really a variation of the Newton-Raphson. All right, now what you're going to do here is that you're going to approximate the derivative with a backward finite difference. All right, now we have to stop for a moment and say, okay, what's a finite difference? How many of you have done any finite difference approximation before? Okay, so very few of you. Where does it come from? It actually comes from a Taylor series expansion. Now, I know that you had Taylor series somewhere in calculus. You went through that, so you probably thought, well, I'll never need that again. I'll forget about it. Well, guess what? You do need them a lot when you get into the upper level courses. So it's time to go back and refresh your memory on Taylor series. This one is a backward approximation. All right, so I'm going to say f of x at I minus 1, some previous value, is equal to that function at x of I minus the delta x, the interval, xi minus 1 to xi, right? Times the first derivative plus delta x squared over 2 factorial, second derivative, minus, now what's this going to be out here?
Compressing everything into one.
Do you see the pattern? See the pattern from the Taylor series? First derivative, second derivative, third derivative, fourth derivative, right? Notice the sign, plus, minus, or minus, plus, minus, plus, minus. All right, get the idea? That's what happens on a backward difference. If I wanted to do this on a forward difference, what would it look like? So I would have x, or f of x I plus 1 equal to f of x of I plus delta x, first derivative, plus that term, second derivative, plus that term, third derivative, and so forth. So in the forward approximation of the series, they're all pluses. In the backwards, they alternate in sign. Now, what I'm going to do is truncate this series. I'm going to say, gee, how far does this go? Anybody want to guess? How about infinity? You know, if you find that, let me know. So you say, hold it, I can't do this, forget that. I'm going to stop this thing. And I'm going to approximate the derivative. Now, let's take a look. So what I'm going to do is approximate this thing. I'm after the first derivative. So here's the first derivative. Here's f of x of I minus f of x I minus 1 divided by delta x plus, now what's this?
0.
What's this mean? See that term right there? That's the carryover from this approximation, right? So that means, what's the order of magnitude accuracy that I have with this approximation? Yeah, it's really first order, because this is the first order approximation. This means second order terms, third order terms, fourth order terms, so forth. Now, why am I interested in carrying just this? That's the highest value of all the succeeding terms, right? When you think about it, if I have delta x squared, delta x cubed, delta x, you say, wait a minute, if delta x is big, those would be bigger values, right? Not necessarily. If delta x, if I'm shrinking delta x, right, then that means those values are getting smaller and smaller and smaller, right? Make sense? This is a concept you have to get in your head here. If delta x shrinks to 0, what have I done? I've come up with the exact equation, right? So I'm not doing the exact equation, I'm approximating. So what I'm going to say is I have this delta x interval, and so that's the error that's going to be associated with this approximation. That's what you get from a Taylor series. This becomes particularly important later on when we're doing partial differential equations. Right? Solving engineering problems as PDEs. Taylor series. Don't throw it away. Circle it. Remember it.
So you're saying the 0 is coming out because you want delta x to eventually be 0?
Yeah. When you think about it in the logic, what you're saying is I'm approximating this function. So I'm approximating it by whatever the interval x of I to x of I plus 1 or xi to xi minus 1, whatever that would be. So when I think about it, if I want the delta x to go to 0, the limit as delta x goes to 0, that's what they taught you in calculus. What's it say? It says, oh, that means all these terms out here would be what? Would be 0. So f of xi minus 1 is f of xi, right? That would be the exact solution, right, or the equation. Okay.
So you're saying we can just leave off the whole part of the equation, or do we still?
No. So this is the series, this is the approximation that you're doing, right, as far as the value at that new location or the previous or the backward value or the forward value, either one. So you're using a Taylor series, and the Taylor series goes to infinity, right? What you're doing as an engineer or a scientist, you're saying, I can't carry all those terms out there. That'd take me till doomsday to solve this thing, right? So what I'm going to do is truncate it. I'm going to stop. I'm going to say, okay, I'm just going to say all those terms are higher order terms, but they're relatively insignificant to the solution. So what I want to know is how close am I coming to the true solution? That's what that term will give you. Okay. We'll come back to this later on.
What about the minus L though?
No, that just means all the higher order terms and so forth. Don't worry about that. It just means that you're carrying, these are terms that would be third order, fourth order, fifth order, all those sorts of
So you
things.
said those equal?
Yeah, what we're going to do is just truncate it. We're going to just eliminate them. All right? So that's going to be the approximation. Okay, so that's what we mean when we say let's approximate the derivative, the first derivative, and we'll use a backward finite difference. Right? So you see how simple it is up here, right? Yeah.
So with this method, we don't actually have to find the derivative if we have some very complex, nasty, ugly, difficult to differentiate function.
That's right. what you're doing is approximating then that derivative with this Taylor series. All right? Now, what do you think Maple or Mathematica or those packages do when they're calculating the derivatives? Sure. They're doing the same thing. The point is, they may carry out a lot higher terms for you. But we just decided right here that we're going to stop after these two terms. We're not going to carry any more terms. All right? Got it? Understand? Okay, so let's take a look. Here's the mass. Let's find the mass of the bungee jumper again. We're going to assume 50 kilograms for the initial mass estimate. All right, so x of 0 is 50. We put it into the formula for the function f of m, right? And we get minus 4.579 or whatever. Okay, so now we're going to go through these steps, right? So really what we're doing is calculating this. All right, so we're going to go here, going to go through this procedure, calculate. This is the delta. Remember the x of I minus 1 minus x of I, right? So now we're going to just evaluate that function with that new interval in there, all right? We can refer to that as a perturbation. Does anybody remember in math, maybe a short lecture on perturbation methods? All right, did you ever have that? Does it ever come up in any of the classes? Okay, maybe later on I will try to give you a little bit of something like that. It should have been somewhere in at least the 4 semesters of calculus and ODEs that you did. The Taylor series is like a perturbation method. And so what you're adding is a small perturbation, that's the delta, right? So the smaller you make the perturbation, right, the closer you're going to get to the exact answer. And sometimes you say, gee, I don't know what kind of perturbation is, so you have to carry out the Taylor series terms. All right, so that's, here is the Newton-Raphson, right, with a slight variation. Now, in finding the derivative with the finite difference, let's look at the values. So 0, right, just in the 0, the first step, just in the first step. You remember what it was for the Newton-Raphson? It was 100. What is it here? 64, okay. What are we down to here? What were we down to in the Newton-Raphson? 10 to the minus 8. Why was that? Because we knew what the derivative was, right, already, so we kind of cheated. We knew the exact value for that derivative. Here we don't.
I have a question.
Yeah.
Once you get like that close estimate, can you rerun it and use that estimate as the guess and then have it get even closer?
That's what you're doing. That's what the computer's doing. If you look at the pseudocode and the M file, you'll see, oh, that's what's going on.
So you just have it run more iterations than the error
Oh,
should get even
actually,
smaller.
yeah, I could have that run much longer. I could say, what's the error criteria that I'm after?
Okay.
And I could say 10 to the minus 8, it may take 5 more steps or something, right? Remember, it's quadratic convergence, even on this method. Okay, so here's the secant method, right? And here is inverse quadratic interpolation. Right? You probably haven't gotten into that just yet. Okay, notice that the approach in B, right, over here, is called inverse. Why is that? Because you're using a quadratic function. It's written in Y rather than in X. Right? So this is, right, that approximation. Here's the actual function. You're going, ah, I see. Okay. So what do I have to do? I have to start shrinking into deltas. That's what I'm reading out. Now, this is what I think is fairly important for you. If you're using the bisection method, or the interval habit, right, then you go, oh, well, it's trying to converge, right? So here is the error between the new value and the previous calculated value. So here's what the bisection does. False position. Here is the secant method, and here's Newton-Raphson. Okay? Now, Newton-Raphson is very effective, providing we know what? The derivative. Right? If we really don't know, we have to use a Taylor series or whatever, then we're really doing a secant. But regardless, They're both under the umbrella of Newton-Raphson. Notice how fast it converges versus these other methods. All right, now let me just mention briefly on polynomials. We'll actually come back to that a little later. Okay, it's a special type of nonlinear equation, algebraic equation. Right? And if you look at this, you'll say, oh yeah, I think I vaguely remember seeing things like this before. Here's a function of x, which is a1x of n, a2x of n minus 1, so forth and so on, all the way down. That L means it's supposed to be dot, 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 but in the fonts on my computer, it prints it as L. So it means, boy, there's a whole bunch of these things, and then I get to the end down here. Right? Now, you may have seen this written the other way around. I know some of you kind of say, oh, I remember it like this, a n plus 1, and going that way. Either way, it's a whole bunch of numbers, right, coefficients. They're routinely used in engineering. Where do we use them? Curve fitting, right? So here's an example of multiple roots. I say the equation has two roots, x equal 3, x equal 1. How many roots does this thing really have? 3, right? X equal 1, x equal 1, and x equal 3. So it really has two roots, but ideally it has 3 roots. Okay. So sometimes a polynomial can be reduced to a simpler form, obviously by dividing by one of its factors. In fact, I think you probably did that 7th, 8th grade somewhere in there. You used to have to do these things by hand. And then you thought, well, I'll never have to see those again. Funny thing about mathematics, never throw it away. Just remember where you can find it. So there are two methods used to find roots of polynomials, Muller's method and Barstow's method. Now, I only will go through these briefly because I want you to say, oh yeah, I remember the names of those things. I remember them vaguely. They're a little more complicated, but every once in a while you're going to run into a package, a commercial package, that says, oh, we're using Barstow's method to do this. And so you'll go, oh, okay, I think I see what's going on here. I kind of remember that method. I'm acquainted with it. Or Muller's method. Okay. So Muller's method is based on the secant method. All right? It uses a parabola instead of a straight line. Notice, when we're doing the Newton-Raphson secant method, we did what? Linear. Right? First derivative. So this says, oh, wait a minute. I'll use a parabola. I'll use the next higher order. So it's instead of fitting a straight line through 3 points, right, it's going to fit a parabola, quadratic. Right? So you can look at the equation, you can go, oh, I see. So here are the 3 points. So what I'm going to do is work my way through 3 points as I go around the curve. Always 3 points. There's another technique that uses that, and it's called a cubic spline. Okay, but it's going to be using a spline, a cubic. All right, so let's take a look. Here's Muller's method. This is what we were talking about before, fitting a straight line. All right, so we go, oops, well, I missed, that's my error. That's what's going to be the error here. So if I go over here, now I'm permitting what? I'm permitting curvature. So if I have something that curves, I go, oh, now I can begin to fit more closely to that curve, what its true shape is, instead of a linear approximation. So your root estimate can be much better. All right, now the other method is called Barstow's method, all right? And here you divide a polynomial by a factor. And I say it's a little bit loosely based on Muller's method and Newton-Raphson. So what you're going to do is guess a value for the root. Right? Then you'll divide by the factor x minus t, whatever that value would be. So you use that as a factor. Determine if there's a remainder. Right? And then Barstow's method then tends to divide the polynomial by a quadratic. That's what makes it interesting. And here's the equation for a quadratic, x squared minus r of x minus s. You can find this method in a number of the library methods or commercial packages. And you'll find that it's very popular, including things like Maple and even MATLAB, for that example. Now, I wanted to just go briefly over these methods that we've discussed so far as a comparison. This was the bisection method, all right? So what are you doing? You're taking the lower guess, upper, divide by 2. You keep shrinking your way in, depending on what the sign is, until you converge to the right value, all right? This is what we mean by a criteria or an error estimation. New value minus the old value divided by the new value. If you evaluate that on a percentage, then you say, okay, if it's less than some value that I established, stop, I'm close enough. Right? If I don't divide by X new, then I have what's called absolute convergence, that is the error criteria. And when I refer to things like 10 to the minus 8, that meant that I was just using this, not dividing by this. Right? Otherwise, I could be grinding out the computer for days to get down to something that would be almost impossible due to round off of the computer. All right, false position. Here's the false position method. All right, notice the linear approximation here. Here's the little formula for that. By the way, what does this mean? Absolute. Why do I want to ensure that I'm dealing with the absolute value? I don't want sign to come into play, because that can really disturb me when I'm doing things on the computer, because it may take things as, oh, you're below 0, so you're okay. And when you realize that, well, it's just a bunch of negative values that are still large. All right, here's Newton-Raphson. X of I plus 1 equal X of I minus F of X of I divided by first derivative. All right, so here's what this is doing. Right, here's the tangent. I shoot down to the abscissa, right? And so what I'm going to say is, aha, that's the 0 value. So what I want to do is say, that error is too large. Let's do it again. And it just keeps working its way down. All right? Here's the secant method. Notice what we've done here. Instead of this, which you may know analytically, we're going to calculate it with the Taylor series, the first approximation. All right, now in an overview here, let's take a quick look at what's going on. If you want to do it by eyeball or direct graphical methods, your accuracy is probably poor, limited real roots. You can actually take more time than a numerical method. All right, so here's bisection. All right, the pluses and minuses as far as the method, what you get from it. Programming effort, obviously easy. Accuracy, it's good. All right, all of these are relatively good. All right, so we get down to Newton-Raphson. What comes out here? It's fast. You got to be careful. It could be possibly divergent. All right, requires evaluation of the derivative. Here is a secant method. All right, same kind of conditions here, medium to fast. Initial guess does not have to bracket the root, okay, as it does up here. All right, so here's Muller's method, Barstow's method. Now I have more methods on here than I discussed, but I wanted to show you the family of these particular schemes that are used for finding roots. And these are the techniques that you will run into in a lot of the commercial packages. But the ones that stick out will be the Newton-Raphson, probably the secant, interval halving, of course, and then Muller and Barstow's plan. Okay, so what's going to happen next week? We'll finish up finding roots. We'll discuss various forms of error. All right, now I alluded to error today, but we'll go over that again on Tuesday. Then we're going to start into the solution of linear algebraic equations. The first one that we'll probably deal with of importance will be Gauss elimination. I think some of you may vaguely remember that when you solved 3 equations simultaneously by hand, you were doing a form of Gauss elimination. Right? That's in chapter 9. Continue to work on your first assignment, of course. If you need to get a hold of me, here's my email address here. You can try to give me a call. We will roll up these lectures as well as the slides onto the website as soon as we get through with this class. Okay, any questions?